This video attempts to unify concepts from these following papers into one clear explanation. I highly recommend you check out these papers, which I will link below after this video. Features are interpretable properties of input data. It's a somewhat loose definition, but I find it helpful to just think of them as concepts. These can be anything from the concept of the Golden Gate Bridge to the concept of antioxidants. Features are represented as vectors in an activation space. In some cases, there is an incentive for these vectors to align with the basis dimensions to minimize interference. After all, you wouldn't want the Golden Gate Bridge feature activating the antioxidant feature. But what if there are more features than there are neurons? To account for this, neural networks learn a neat trick called superposition, where they squeeze in features that would be orthogonal in a high-dimensional space to be almost orthogonal in a low-dimensional space. This is possible because of a property of high-dimensional spaces. Although you can only have n orthogonal vectors in an n-dimensional space, you can have e to the n almost orthogonal vectors in an n-dimensional space. This is great if we want these models to learn well, but bad for us if we want to interpret these models. This is because these neurons are over-representing features. So when we pass in any input, such as one about antioxidants, almost all of the neurons will activate. When we do the same for the Golden Gate Bridge concept, these same neurons also activate. In other words, everything activates everything. This brings us to our fundamental question. How do we make polysemantic neurons monosemantic? It's important to note that this is a very hard problem, as we're essentially trying to recover a high-dimensional vector from its lower-dimensional projection. This is sort of like trying to recover an image from its very compressed form. But there is a way we can try to do this using something called sparse autoencoders, which uses two key aspects: an expansion factor and a sparsity constraint. An autoencoder you may be used to saying compresses the input because there's physically less space in the hidden state than the input dimension. The sparse autoencoder does the opposite, giving a plethora of space using an expansion factor. Mapping a lower dimensional space to a higher dimensional space helps disentangle the packed-in almost orthogonal vectors. So that's one step, but how do we want to make sure that our problem of everything activating everything doesn't continue? We can add a sparsity penalty to activations. Let's say our dataset contains three features: antioxidants, the Golden Gate Bridge, and water bottles. Without a sparsity penalty, all of these neurons will activate for each input. But with sparsity, the network is incentivized to arrange features in a way that only a few neurons activate for each input. We can train our sparse autoencoder by selecting a layer in our language model to take activations from, and then passing our dataset through the language model. Each forward pass, the activations from this layer will be sent to the sparse autoencoder, where they will be sparsely represented, and then reconstructed back into their original form to travel through the remainder of the language model. By the end, the sparse autoencoder will ideally learn a disentangled representation of our features. From this, we can do many interesting things. Let's say we pass through an input that contains all of our example features, such as I take my water bottle to the Golden Gate Bridge and eat antioxidants. By analyzing what sections of the sparse autoencoder light up, we can see what sections of it correspond to which features. And because activations we input to the sparse autoencoder are actually the model's internal computations, the sparse autoencoder can tell us in a sense what a language model is thinking. We can also use the SAE to steer outputs. Let's say that we want to forbid our language model from talking about antioxidants. We can permanently clamp that section of our sparse autoencoder to 0, which will then be mapped back to the activations that pass through the rest of the language model. What if we wanted to make sure that our model always talks about the Golden Gate Bridge? Well, we can clamp that section of the SAE to a very high value so that the Golden Gate Bridge feature is highly activated in proportion to other features. Practically, this can translate into important safety work. Because these models are trained on the internet, they can pick up harmful concepts such as lying and deceit. If we can find these features and then clamp them to 0, we can mechanistically ensure that these models don't deceive humans. What if we wanted to make sure that a language model always outputted a JSON? We can clamp the JSON feature to a high value, making our model more reliable for our use case. So by disentangling features, we gain a lot of new tools to make language models safer and more beneficial. If you found this explanation useful, consider liking the video. If you have any questions, feel free to drop a comment below. And until next time, remember that papers are wonderful.